When you find a point of tangency, you want to choose a point as close to 14 as possible that's a perfect square. So what did you do? 16, 4. The slope is not just some floating nonsense. It needs to be clearly identified. The slope is the derivative at 16. If the function is the square root of x, then what's the derivative? 1 over 2 square root of x. Pay attention to notation, please. This is a lot to get used to, okay? So what I just wrote there is a lot. What's wrong? Okay, this says the derivative at 16, which is a specific case, and this is the general derivative. Those are not the same. And are they that picky that they would nail you for that?
Yes.
Yeah. That's not true. And they care if you say something that's not true. So if you say, I intend to evaluate that at 16, then you say this evaluation bar is how it should be properly denoted. And did you get something like 1/8 for the slope? Okay. The equation of the line is y minus 4 equals? Perfect. Now, if the question said, make a tangent line to the curve at 16, am I good to go? I'd be done. But that's not the question. The question says, use your tangent line to estimate. So now we have to do one more thing. We have to put 14 into our tangent line. Y is 14 plus an 8 of 14 minus 16. That's 14 plus an 8 of -2. That's 14 minus 1/4. And so our estimate is? Oh, yes, you're right. I would have eventually caught it because that's a terrible estimate. The square root of 14 is not 14. It's 4 minus 1/4, which is 3 3/4. Okay. True or false if I wrote my answer this? Not true. Do they care if you say something is equal when it's really an estimate? Yeah, they care, and I care. All right, so that's not true. The y on the line is truly 3 3/4, but as far as the square root of 14, it's an approximation. All right, so how are you doing on tangent lines? Are you successful? Okay. Let's talk differentials. Give me an example of a differential. dy, perfect. dx, what is a differential? Plain old English. A tiny change in some variable, right? Perfect. Okay. So, if I want to do a spherical cake pop and they're talking about change in volume, then what's the equation to use? Pi r cubed. Perfect. All right. Now, the big idea of yesterday is you can estimate true change, which is the actual delta V, with a differential, which is dV. And dV comes from taking, saying, well, dV dr is V prime, and moving that over. So dV is V prime. Let's get a little more specific. V prime at what? At what? At R initial, okay? And I probably should have done that more yesterday. I started writing that in third period, and it made a lot more sense. And then times d r. Are we? All right, now let's get into the details. If volume is 4/3 pi r cubed, then what's V prime? 4 pi r squared. And at what value will we evaluate? 2. And what is dr? Is it plus or minus? Will volume increase or decrease? Is the radius increasing or decreasing? Increasing, because the volume is going to get bigger when we dip it into frosting. That sounds delicious. It's positive 0.1. And so what is 4 pi r squared evaluated at 2? 16 pi. And what's 16 pi times a 10? 1.6 pi. And what are the units? Centimeters cubed. So roughly about 44.8-ish, 5-ish cubic centimeters of frosting on that baby. All right, are we good? All right, today's lesson is a pre-calculus lesson. I hope that the tangent stuff, cosecant stuff will just be review. I don't honestly know if you guys did reciprocal graphing in the most general terms last year, so I'm not sure what the deal is though. So tangent, cotangent, secant, cosecant, they're just small examples of a bigger world of what happens when you graph the reciprocals. What happens when you put that thing in the denominator. So let's think generally. Where the graph of f has an x-intercept, which would imply that the function is 0, then 1 over f will be 1 over 0, and therefore undefined. And what will that mean graphically? There's a vertical asymptote. So where the original graph has a 0, the reciprocal graph will have a vertical asymptote. This is pretty reasonable, I think you'll agree, but what's the reciprocal of positive 2? Is it 1/2 or negative 1? 1/2. Can you take the reciprocal? The sign does not change. Okay, so there's always a student. I thought you switched it and switched the signs. What do they think about? I think they're thinking parallel lines. When you do parallel lines or perpendicular lines, isn't that switching again? Yeah, that's not what we're doing here. Okay, so it's just the reciprocal of a positive is a positive, and the reciprocal of a negative is a negative. So where the graph of f is above the x-axis, the reciprocal will be above the x-axis. If the original is positive, the reciprocal is still positive. That doesn't change. A little more abstract. Where the graph of f is small, which would mean close to the x-axis. I don't mean like, I graphed it small. I mean the y values are small. Well, 1 over f then is 1 over small, which is big, and therefore it'll be far away from the x-axis, or large y's. The reciprocal of small y's is large y's. By the same token, where the graph of f is large, which is to say a big y, far from the axis, the reciprocal will be 1 over large, which is small, and therefore close to the x-axis. Keep those ideas in mind as we graph these two things. First of all, would you show me that you remember how to graph factored polynomials? What is the overall shape of this? Ouch. If I expanded this, what's the lead coefficient, lead term? Negative x cubed. And so that shape is either this or this, right? And what does factored form tell you? Zeros. Yeah, tell you zeros. So you should know the shape, you should know the zeros. Ain't that way up? What happens at a squared 0? Why? Because it's squared, there won't be a sign change there. Wouldn't you agree that before squared, it's negative, squared, it's positive, after squared, positive, squared, it's positive? There's no sign change from there. So it's bouncing, yes. So it's bouncing off 2 and 3, yeah? They're so close together. Oh, well. So, did you get something like this? Whoop-a-dee-doo. I wish I would have had those a little further separated. Are you down? Okay. Now let's talk the reciprocal. Give me one thing you know. Our f has zeros. The original has vertical asymptotes. So I'll have vertical asymptotes at 2 and 3. Maybe I should have changed my scale to go by half so it's a little wider, but oh well. All right, tell me about less than -2. Less than -2, the function is positive. Therefore, less than -2, the reciprocal is positive. So I know it's going to be up here. Yeah? All right, somewhere. Let's talk shape. As this gets really, really big, these are really big y's, the reciprocal will really be small. For example, when y is 8 here, the reciprocal will be 1/8. It'll be tiny. So take some reciprocals, and this will be very small instead of very large. What about here? As we get close to 2 from the left, the y values are getting small. The reciprocal then will get big. For example, here, the y value is like 1/10. Well, the reciprocal of that is 10. So it's going to shoot up like that. All right. What's it going to do between 2 and 3? Above or below the axis? Above. And what kind of shape do you reckon? Where these are small, these guys will be big. It looks like I didn't get into how high it goes, but how high does it look like my y is? 1/2. So what's the reciprocal of 1/2? 2. So I'm feeling somewhere like in here. Oops. I need to sharpen my marker, but something like that, yeah? And last but not least, right of 3, where the graph is negative, the reciprocal is negative, and so what shape is going to be down here? Give me some of this. Let's don't do that. Okay, good job. Boom. And should it curl back away from the asymptote? No, my graph is terrible because it failed the vertical line test. It should approach the asymptote. Darn it. I'm not very coordinated. That's why I'm a math teacher. All right. So, there you go. There's the graph. You with me? All right, let's review 6 trig graphs. You should be able to graph all 6 trig functions. I'm going to emphasize once more what I want to see. I know I've done sine and cosine, so this should be a review. First thing you should do is factor if it's not factored form. Saxon rarely messes with you here, but I will. So this needs to be factored. If you factor out a 2/3, then what's left? X minus 3 pi over 2. You can always check and say, if I distributed, would I be good to go? If I distributed, would I be back to where I was? Yeah. Okay, now it's crucial that you do that, because if you don't, look in here, what are you going to think the shift is? Pi. It's not pi. It's 3 pi over 2. The whole shift is dependent on the attack. So, what's the quote-unquote starting point? This should be quote, start. If it's normally at 0 and it got shifted right or left 3 pi over 2, then it's 3 pi over 2. What's the period? How do I find the period? 2 pi divided by the 2/3. So what is the period? 3 pi. Or if you like, 6 pi over 2. So we're starting at 3 pi over 2. We're traveling 6 pi over 2. Where do I, quote unquote, end? 9 pi over 2. A wave will end at 9 pi over 2. One more thing here. I expect accuracy at every quarter wave, as we talked about. So let's talk about a quarter wave. If a full wave is 3 pi, then what's a quarter wave? 3 pi over 4. All right. Now, with that said, if I want to start at 3 pi over 2 and travel 3 pi over 4 each time, then maybe it would be best to use a scale of pi over 12, I guess you could say, but I was just going to say pi over 4. So what's 3 pi over 2 in pi over 4 terms? 6 pi over 4. Okay, so here we go. Actually, and then what's the min? What's the center line of that? I should have maybe said center line. What's the center line? 0. What's the amplitude? 1. And so it goes from -1 to 1, and a sine shape, negative sine shape is that, yeah? Okay, so here we go. We're going to start at 6 pi over 4. 1, 2, 3, 4, 5, 6 pi over 4 is right here, yay? I might need to fill back some. So every quarter wave is 3 pi over 4. So if you just count, do you mind if we make our scale half on the vertical so it's not so tight around the axis? All right, so to find this second point, I'm going to go 3 pi over 4s. So that's 1, 2, 3, and that'll be a min. At that point, I'm a little out of room, so let's go backwards. When I go back 1, 2, 3 pi over 4 from 6 pi over 4, doesn't that take me to 3 pi over 4? And that's a max. And what else do I got? 3 more boxes takes me to the middle. 3 more boxes to the left takes me to a minimum. 3 more boxes to the left is middle. 3 boxes to the left is a max, and then I'm kind of out of room. And I expect you to graph over the entire space provided. You follow me? Try the second one on your own, or with your math amigos. How are we doing? Finishing touches, about good? Did you get a period was 12? Nope, 24?
Yep.
That's kooky, but it is what it is. That is going to make it hard, given that I only have like 20 boxes wide to get a full period on. That's all good. Did you go by 1s or 2s on the horizontal? Either one is fine. Which, just shout it out what you did. All right, 1s is fine. If you did 1s, your period you won't probably get a full wave on there. That's fine. I'm gonna go by 2s. That's pretty good too. I'm fine either way. Do you agree that the center line is 2 and the amplitude is going to take you up to 6 and down to -2? All right, cool. So my vertical scale is 1 and my horizontal scale is 2. And let's begin. This is a normal cosine wave, positive, so peak to peak, and the starting point is -1. So that is there. And then if I go, gosh, I feel like maybe ones would have been better. Now it's a half box. That is what it is. All right, so each quarter wave is 6, so that's really 3 boxes. So 1, 2, 3, middle. Do you have a middle point at 5, 2? Yes? 1, 2, 3 boxes minimum. Do you have a middle point or a low point rather at 2, 4, 6, 8, 10, 11, -2? Yes? You should. 1, 2, 3, middle. Alrighty. So, is that graph okay? It is not. If you don't graph over here, what are you telling me? There are no points over there, and they're off. And so you should graph there. 1, 2, 3, middle. 1, 2, 3, min. 1, 2, 3, middle. It should look something like that. All right, let's go to a little more complicated in that now we're going to have cosecant. Most of the work is exactly the same. Then we're going to talk about what cosecant does. So we'll start graphing 3 sine x minus pi over 4. What's the quote-unquote starting point? What's the period? 2 pi. What's the ending point? If we start at pi over 4, go 8 pi over 4, then that ends me at 9 pi over 4. If a full wave is 2 pi, then what's a quarter wave? Pi over 2, which I'm going to go 2 pi over 4s, because I think I'm going to use pi over 4 as a scale. You follow me? Okay? What's the center line? 0. What's the amplitude? So what's the min and max? -3 to 3. Okay? Let's slightly dot in the shape then. Cosecant is a reciprocal positive sign, so this is the shape, yeah? So I'm going to start at the middle at pi over 4. That's my quote-unquote starting point. And I said each quarter wave is 2 pi over 4. So how many boxes do I travel for each new point? 2. So when I travel, oops, that's the center line right there, dum-dum. Sorry, it should be at the axis at x of pi over 4. When I travel 2 boxes on a positive sine curve, that takes me to a max. 2 more boxes takes me to center line. 2 more boxes, min. 2 more boxes. It feels like I end my graph about the center line. Going backwards, 2 boxes from pi over 4 to the left takes me to a min. 2 more boxes, middle, max, middle, min, and I don't quite get to back to my middle. Okay? Now, if you want to lightly dot that in, fine. If you want to leave that out, fine, but the objective is not to graph sine, it's to graph cosecant. So, we know that cosecant has asymptotes. Why? Why do secant and cosecant have asymptotes? Yeah, there's a possibility of, because cosecant is over sine, where sine is 0 in the denominator, you're going to have a problem. Okay, so you have vertical asymptotes. Where do you have vertical asymptotes? Give me 4 of them. Pi over 4, 2, 3, 4. 5 pi over 4, 6, 7, 8. 9 pi over 4, -3 pi over 4, whatever that is, -7 pi over 4, and so on. It's a big dotted mess, yeah? Last but not least, the shapes of cosecant. We said that when the sine gets small, the cosecant gets big. So I'm going to have a positive U shape at any max where I was also positive, and I have a negative downward opening N shape, I guess you could say, touching any min. You follow? Okay, try the next one. Doing for a scale here, 1 box to pi over 4 or 2? Every quarter wave is pi over 4, yeah? So if you make your scale pi over 4, your waves are going to be pretty tight. Do you want to go with the pi over 4 scale, or maybe 2 boxes to a pi over 4? Alright, I would suggest if you want this to be a little less busy, maybe go 2 boxes to pi over 4. Okay. Let's see how you did. Look at where your asymptotes are. Do you have an asymptote at pi over 4? And 3 pi over 4? And 5 pi over 4? Do you have a curve that's right at the y-axis at a minimum of 0, 6, opening up? Or do you have one at 2 pi over 4, negative 2, opening down? And 4 pi over 4, 6, opening up? And that's pretty much it on that side. On the negative side, maybe negative 2 pi over 4, negative 2, opening down, and negative 4 pi over 4. Yes? I didn't actually start here. This was the first point I graphed. That kind of came from me backfilling. So the starting point was 2 pi over 4, and so that's this point. And then every quarter wave back, so it looks kind of like a sine wave. Okay? Okay, last but not least, let's talk tangent and cotangent. At the very least, we'll get through the examples, maybe not the practice. Why do tangent and cotangent have vertical asymptotes also? Yeah, tangent is sine over cosine, and this would be undefined if cosine is 0. Likewise, cotangent is cosine over sine, it would be undefined if sine is 0. And as you get really, really close to 0, you got small in the denominator, that gets big. That's why it goes so infinitely hard. What's the normal period for tangent and cotangent? It's not 2 pi, it is pi. A normal tangent. Think, wouldn't you agree that sine over cosine and cosine are the same as y and x, which I should have switched. So if we look at the unit circle, isn't it 1, 0 there, 0, negative 1, negative 1, 0, and 0, negative 1, yay? That's what I said. Where? 0 positive. Oh, this is positive 1? Good call. Yes, you're right. Okay, so tangent is cosine over sine. So at 0, cosine over sine, or sine over sine over cosine is 0 over 1. Is that allowed? Yeah, it's 0. Okay? What about at pi over 2? Cosine over sine is, sine over cosine is 1 over 0, which is undefined. If you went down to negative pi over 2, isn't that also undefined? You follow me? All right. It is important also that you locate to me not just the middle point, but the quarter points. Just like in a sinusoid, I want the quarter points. So for example, when you take the tangent of pi over 4, what do you get? 1 and negative 1. Now to me, those are important because that's what communicates if it's been stretched. If I see a graph that has those quarter points up at 3 and negative 3, that tells me there's been a vertical stretch, and instead of tangent, it's 3 tangent. So these points are necessary to communicate vertical stretches. I need those quarter points. Understood? Cotangent is cosine over sine. So it's 0. Sine is 0, so we get 1 over 0, which is cotangent's undefined at 0. At pi over 2, cosine over sine is 0 over 1, which is 0. And at pi, cosine over sine is negative 1 over 0, which is undefined. Does the shape go up to the left or down to the left? Down to the right, up to the left, it goes like this. Why? Because some guy said that's the way it should go? No, because the cotangent of pi over 4 is 1, positive 1. It's got to go that way. It's no, they just thought it looked pretty. Okay? So, with that in mind, 2 tangent of 4x. What will this do? 2. Vertical stretch. What will the 4 do? Changes the period. Okay, so the period now, instead of being pi, it'll be pi over 4. It's a horizontal compression. So let's go with, so if it's pi over 4 period, then instead of this asymptote being at pi over 2, it's pi over 8. Okay, so let's go pi over 8. I'm going to put that 4 boxes out, and negative pi over 8 is 4 boxes left of the axis, and those will be asymptotes. If you're not sure, if you were quiet while they said pi over 8, think about it. Cosine of 4x in the denominator would equal 0 when 4x is pi over 2, which means you'd have a problem when x is pi over 8, right? So if you're not sure where the asymptotes are, say tangent is sine over cosine. I have a problem where cosine is 0. Solve that little equation. All right, so I have pi over 8 at 0. What's tangent, 2 tangent of 0? 0. Way to go, me. At pi over 4, what's 2 tangent of 4 times pi over 4? Nope, pi over 4. What the heck? What's half of pi over 8, dum-dum? I was talking to me, not you, sorry. At pi over 16, what's 2 tangent of 4 pi over 16? Well, tangent of 4 pi over 16 is tangent of pi over 4. That's 1 times 2 is 2. I'm going to go by just ones. Alright, so now I feel like I've got the shape nailed down. Am I good with one graph? No, Mr. Strickland's a jerk. He requires you to graph all the way to the edge of the space. So, think this way. On this side of the asymptote, didn't I go 2 boxes to a point? So on this side, won't I go 2 boxes to a lower point, 2 boxes to a middle point, 2 boxes to an upper point, and as much of the wave as you can get? You follow? Now you try on the far left side. 2 boxes left of the asymptote, is that going to be a higher point, a middle point, or a lower point? Something like that. Pretty cool? Nope? Yes? Good? Okay. In the interest of time, we'll blow off the rest and we'll see how it goes. All right. Questions on homework from last night? I did post some work problems for both yesterday's and our last night's homework in the calendar, so I don't know if anybody saw that. I actually had my act together myself. Let me know if you have questions on set 29. 14. 14. Others? Somebody? No? 29. 14. 8. We could also do the replacements, I suppose, if you want to, although they are posted. The replacement answers are posted. Okay? All right. I will be happy to take other questions, but let's start there. 14. First of all, I did change the problem a little bit, which I am prone to do, so I hope you didn't just blow off that. It says find the slopes of the tangent to each curve at x equal 1. The problem in the book was find the center, which is a fine pre-calculus problem, but I would rather you do some calculus. So 14, the idea is given 4y squared minus 9x squared minus 8y plus 36x minus 68 equals 0. I want you to solve for y and then find the tangent slope at x equal 1. Okay, so when I solve for y, do you agree that I want the y's together and everything else on the other side? Cool. So if I do that, I get something like this. Oops, minus negative 36x plus 68. That 4, do you divide it and leave it out front, or do you divide it all the way over? Okay, so y squared minus 2y equals 9 fourths x squared minus 9x plus, what do we got there, 17? Yeah? Okay, now let's complete the square. What goes there? Plus 1, which I must balance by adding 1 over there. So y minus 1 squared is 9 fourths x squared minus 9x plus 18. Oui. All right. So then y is, when I square root is plus or minus and move the 1, isn't y 1 plus the square root of 9 fourths x squared minus 9x plus 18, or 1 minus the square root of 9 fourths x squared minus 9x plus 18? You concur. Cool. All right then, now the calculator component. If you would, bless you. I don't want to take the derivative on that because it's hideous and is chain rule, and we haven't done the chain rule, so we're going to do the
Derivative by calculator. That's what I said, meant when I said find the slopes. I mean, use the calculator to find the derivative at the indicated point x equal 1. So, I would personally put this in F1 and F2. Okay, so here we go. In F1, I've got 1 plus the square root. Obviously, this is a mess, so be careful. 9 divided by 4, x squared, I believe. And then there's something else there going on. What else was it? Minus 9x plus 18. Minus 9x plus 18. Boom. Do you get something like that? You with me? Okay, so it feels like hyperbola. I'll do the negative in a second. I'm going to, rather than type it again in F2, I think I'm just going to leave this, do the derivative, and then go back and change the sign to negative, and so I don't have to type so much. You with me? Are you with me?
Yes.
Cool. So how do I do the derivative at a point? Menu, 4, 1. The function is x. The value I want the derivative at, according to the question, is 1, I believe. All right. The function I want to use is f1. And so the upper curve slope, I get negative 0.6708. Are we down? Okay. Now, let's do the minus case. Go back to your graphing menu, hit tab, scroll up, and change the add to subtract, and hit enter. It changes the curve to lower. Now let's go back, and rather than retype all that, can I just scroll up and recall that command and hit enter again? And it'll calculate the new f1. So my two derivative values are negative and positive 0.6708. Very cool. Actually, I'll just go y prime at 1 is negative 0.6708. Y2 prime at 1 is positive 0.67. Cool. All right, 8. Question on 8. Is that still a question, people? All right. All right, show all derivatives, making sure you show your work properly. So the idea is y equals sine of x. Did I say you had to use the notation or you can dump it? All right. So Leibniz notation is a little intimidating to students. They say, oh, life is good. Well, you better get over it before you take different Q, but it is what it is. If you would prefer to do just y prime, that's fine. That is a thing. So what's y prime? Cosine of x. What's y double then? What's the derivative of the derivative? So the derivative of cosine. Okay, what's the third derivative? Y triple. Negative cosine of x. So what is y triple at 3.5? Well, that's not pretty. Cosine of 3.5 radians, I don't know, close to cosine of pi, so close to negative 1, but probably not negative 1. So I would imagine it's something. Type it in, call it good. All right, say it again. 0.936. Oh, thank you. Okay, awesome. So close to 1 makes sense. Any other questions you'd like to talk about? Wow, you guys are splendid. I'm going to verify that I do have some hints slash work for you to look like. If in my calendar, sometimes I forget. But I think if you look at 29 in more details, I think I put some problems. Ignore 3. That was from a previous year. I replaced it, so don't do 3. But there are some problems worked out. Okay? Okie dokie. Have a lovely day.